Pearson.
A great day to one and all again, and welcome to this beautiful morning. And today we will proceed with another parametric test. And this is all about Pearson product moment coefficient of correlation, or in short, we can call this Pearson's R. I am Kim JC Ensure, and I am your course facilitator. So the majority of my talk is taken from learned statistics. And for the past days, now we have talked about significant differences. And we talked particularly about independent samples t-test, dependent samples t-test, and one-way ANOVA or analysis of variance. So those parametric tests are used not to determine if there are significant differences. So I also discussed with you yesterday, or cleared. No, hopefully, I was able to clear out the misconception, or I mean the differences as well between independent and dependent samples t-test. And also yesterday, I talked about one-way analysis of variance. Normally, if you would like to determine if there are significant differences between two groups, two independent or different groups, we can use t-test for independent samples. But if you have three or more groups, then you can
ANOVA.
use one-way ANOVA. But again, provided that we satisfy all the conditions on the use of these parametric tests. So this time, we will go away with significant differences, but we will go with relationships. Okay? Let's talk about how about can we determine if certain two variables are significantly related with one another or not? Now, okay? So here's the introduction. The Pearson product moment correlation generates a coefficient called the Pearson correlation coefficient, denoted as small letter r. That is the italic lowercase letter r. This coefficient measures the strength and direction of a linear relationship between two continuous variables. So again, when we say continuous variables, these variables are either interval, both of them are interval, both of them are ratio, or one is interval and the other is ratio.
Okay.
Take note that you can use if your data is nominal and or ordinal, then Pearson product moment correlation or Pearson R is not applicable to test the relationship between two variables. The value of this could range from -1. -1 stands for a perfect negative relationship to +1, which is a perfect positive linear relationship. Okay. So you might be wondering, what does a negative relationship mean? And what does a positive relationship mean? Okay. For example, let's say I will talk about two variables. The first variable is number of apples bought, and the second variable is payment mo or yung bayad mo. Okay. If you buy more apples, what do you expect with your payment? Will it increase or decrease?
Increase, sir.
Maybe increase, sir.
Increase, sir.
It will
Increase,
increase,
sir.
right?
Yes,
The
sir.
more apples bought, the more you have
The
to pay.
more.
How
Yes.
about if you buy fewer apples? What do you expect of your payment?
Increase.
Decrease,
sir.
Decrease.
Your payment will
Decrease.
decrease as well, right? So you see, the first variable, as the first variable increases, the more apples you buy, the more you have to pay. The less you buy, the less you have to pay, right? So you
Yes,
could
sir.
see they go in the same direction. That is an example of what we call positive or direct relationship. Meaning to say, when we speak about positive or direct relationship, it means that as one variable increases, then the other variable also increases, no? Saka, it's either up, up, or down, down. They go the same direction. That's what we call that's what we call positive relationship. But what about negative relationship? When we speak about negative relationship or indirect relationship, the two variables go in opposite ways or direction. For example, meaning to say, if one variable increases, the other variable decreases, and vice versa. If one decrease, the second increase. They go in opposite directions. Okay? For example, let's talk about speed and time. The speed of the car and the time for you to reach your destination, assuming that there's no traffic. If your speed becomes faster, then the time for you to arrive to your house becomes smaller, right?
Correct.
However, if your pacing or if your speed becomes slower, then the time for you to go to your house, for you to reach your house, becomes higher. That's why you could see they go in opposite directions. So speed of a car and the time for you to reach home, these two exemplify negative relationship because they go in opposite direction.
Opposite direction.
Now, a value of 0 means that there is no relationship between the two variables involved. This statistical test is often known by its shorter title of the Pearson correlation. You could also say Pearson's correlation or simply Pearson's R. Okay. So again, the closer the values you get to -1 or -1, the relationship becomes stronger. But as the value of R that you get becomes closer to 0, then the relationship becomes weaker and weaker. And if you reach 0, meaning to say the two variables are not really related with one another. So I talked about positive, no correlation, and negative. Normally, in many instances, if we study our students, for example, or if we wish to determine relationships of two variables when taken from humans, most of the time, it's rare to achieve perfect positive or perfect negative relationship. But most of the time, it's either positive, negative, or no correlation at all. Okay. Now, for example, again, that's why there's a question mark there because I'm not sure. But there are some studies that states that math and science scores are positively or directly related. Do you agree with this? It means if math scores, they say if you are good in math, most likely you are also good in science. The higher the math scores, the higher the science scores. Or if your math is low, your science is also low. Do you think it's true or not? Do you think it's really positive or not? What do you think?
Maybe.
Do you agree with this? Or, sige be, if you don't mind, would you mind commenting in our chat? Do you agree that
Depende.
math and science are...
Depende.
Depende
So,
sir
if you
kay
don't
Mera, may math man nga taas niya grades no sa science
answer
ka
in
no
our
bubuti
chat?
siya.
Yeah.
Yeah,
Oh, depende. Depende,
But
sir.
if we could take a look, but what I'm asking in general terms, do you think this is positive or not? Please comment in the GC, please. Okay.
Maybe.
According to Ma'am Abby, true daw. She agrees that it's positive. Okay, how about the rest? Take note, ha? I am not only, of course, there are some exceptions to the rule, but in general, do many cases support this idea? What do you think? Okay, maybe positive. Says Ma'am Rona as well. Positive, okay. Some students can be good in science, they can comprehend well, okay. Okay, so some of you would say it depends. So many of you would say, uh, maybe you don't agree, maybe. Okay. I believe that there's no correlation because I don't know. I think there's no correlation between the width of the forehead and intelligence. Remember our forefathers before, our grandmothers, our grandfathers would tell us sometimes they would believe before that if okay, no, in local terms, if they say kung lapad ang dahi mo, meaning maalam ka. Do you think do you think that's true? Is it really related? In your opinion, does it follow that if your forehead is wider than others, does it really mean that does it really imply that you are intelligent? Is it positive, negative, or no correlation? In my
No
case,
correlation, I think.
I think there's no correlation.
Yes.
For me, honestly,
Yes, yes.
uh, I
What's the connection?
I think for me there's no connection.
Yes.
Okay, that's why I think that I disagree with this. That's why I place no correlation. So if
Yes.
there's no correlation, meaning there's no connection between the two.
Yes.
But if I say positive or direct, meaning if one increases, then then increase
There's a
increase
tendency.
or decrease decrease. That's positive or direct. Yeah. So for me, this is what I believe in. I think they're not related. But again, it's just my own opinion. And I firmly believe as well, no, as what I mentioned earlier, negative relationship. Example, we have speed and time. Okay. Okay, how about this? I'll give you two variables. Do you think it's positive, negative, or no correlation? Okay, width and height. Height and weight. Height of a person and his or her weight. Do you think it's positive, negative, or no correlation?
Positive, sir.
Okay, please comment your answer in RGC. I would like to see your answer. Height and weight of a person. Because if you say positive, meaning if you think in general, if you think that if a person becomes taller, then his weight then he also becomes heavier. That's what you're thinking. But if you could say negative relationship, if a person becomes taller, then the weight becomes lower. Do you think it's positive or negative? Height and weight. Okay, let's see. I'll read now some of your comments. Okay, some of you says positive. Some of you says negative. Okay. Someone also said no correlation. Okay. So this is kind of interesting because in your case, some of you believe positive, some of you believe negative, some of you believe they are not related at all. But the thing is, if we really wanted to establish if there is a relationship between the two, then as researchers, we should gather evidence.
Yes.
Maybe we could do random sampling, gather data from a random sample, gather their height and weight, and use Pearson's R to determine if there is really a significant relationship between them, or to determine also if they are indeed related or not. That's why there are some variables that are quite controversial probably, but if we wanted evidence-based conclusions, we need to base it on actual data. So here is an example of what a perfect negative correlation looks like. So it's from -1. They lie on a perfect straight line that falls to the right. So you see, they all lie perfectly on a line. If you have R of -0.8, this is an example. The data points are a bit scattered, but it still suggests that the line is falling to the right. No?
Mm.
So this is an example of r equals negative 0.4. So you see, as the value of your r becomes closer and closer to 0, the line at the points or the data set becomes more and more scattered. But here, somehow, it's scattered compared to r equals negative 0.8 and r equals negative 1.0. But somehow you could see that it's going down somehow, right? It's still going down. If you reach an r equals 0, if r is equal to 0, take a look. Take a look at this set of points. Can you tell if the line is going downward or going upward? As if wala,
Upward.
right? You could, for example, sa letter D, it's as if there's no line. That in this case, the line is suggesting downward. Here, does the line suggest upward or downward? It's as if you cannot tell, right?
Yes.
So most likely,
Parang
that's
ano
why
sir, upward.
Upward,
this one,
downward.
this
Upward,
letter D,
downward, sir.
Good line,
Letter
sir.
D.
you cannot
Fine,
tell.
too.
In my opinion, you cannot tell. That's why if r is equal to 0, the points are too scattered that you cannot tell if it is going upward or downward. That's why there's no relationship if r is equal to 0. But if we take example, no, for r equals 0.6, if you take everything here, it's scattered, but somehow I could see a line that, I mean, the thread is a bit going upward. And here for r equals 0.9, it's going upward still. And if you have another r here, which is equal to 1.0, positive 1, I'm sure they will all lie on a perfect straight line. So you see, the closer it is to either 1 or negative 1, then the more dominant the line is, no? The more you could see, the more they cluster to fit a line. But if the value of r is getting away from 1 or negative 1, or it approaches 0, for example, then the line becomes less prominent and less visible and cannot be identified easily. Questions so far? None? Okay, thank you. Thank you. So there are two variables required, no? Two variables that are at least in the interval or ratio level are needed for you to determine if there is a significant relationship between them. For example, weight and cholesterol. Okay, do you think that weight and cholesterol are related or not?
Yes.
Weight and your cholesterol and our cholesterol.
Cholesterol.
Do you think it's
Related, sir.
positive, negative, or no relationship?
No relationship, I think.
No relationship. So wala daw
Positive.
relationship ang weight at cholesterol. Ma'am Abigail said positive daw. If you are saying, Ma'am Abigail, if Ma'am Abigail is saying na kung positive, as weight increases, cholesterol also increases.
Okay.
Or the other way around, no? If you lose weight, your cholesterol level also becomes lower. That's positive relationship. Up,
Yes,
down,
sir.
down. But if you are saying negative, as weight increases, cholesterol decreases. I disagree with that. I think, in my opinion, I think it's not negative. I think. Because I'm not sure, but based on my observation, as weight increases, I believe that generally the cholesterol, does not decrease. I think so. None daw? Okay, so many of you answered positive. Okay. But again, we need to gather actual evidence, so gather actual data before taking their relationship. Now, so what problems can be solved using Pearson correlation? Letter A Pearson correlation is most often used to discover the relationship between two variables. But take note, linear relationship only. If they if there is a line. Okay? In this type of study design, you have measured two variables that are paired observations, and you wish to determine the strength of the linear relationship between these two paired variables. For example, is there a linear relationship between height and basketball performance? Do you
Yes.
think? Kaya hambal nila or sabi nila kasi, kung mataas ka, kung ang height mo increase, or let's say habang tumatangkad ka, yung performance mo sa basketball nag-i-increase din. Sabi nila positive daw yon. Does it mean wala kung putot ka, ang imo performance compared sa iban lower? Parang ganun, no? But you could also ask, is there a significant relationship between
Between height.
height and basketball performance? Yan.
May advantage yun.
So here are some of the assumptions in before we use Pearson's correlation. First assumption, which is the usual assumption of all parametric tests, of many parametric tests, I mean, your two variables should be measured at the interval or ratio level. That is, they are continuous. Okay? That's why interval or ratio only. Both of them interval, okay? Both of them ratio, okay? One is interval, one is ratio. That is also okay. Clear? Next assumption. There needs to be a linear relationship between the two variables. The best way of checking this assumption is to plot a scatter plot and visually inspect the graph. The third assumption is there should be no significant outliers. So outliers, remember, these are extreme scores, right? So if possible, if you have outliers, we could usually have them taken out of our data set if possible. The fourth assumption, if you wish to run inferential statistics like having our null hypothesis, you also need to satisfy the assumption of bivariate normality. Okay? And some of these other assumptions were taken from other sources. There should also be, the fifth one is, if possible, the assumption of normality. As much as possible, your data is normal. The sixth assumption is that there should be what we call homoscedasticity, which means that the variance along the line of best fit remains similar as you move along the line. So if you could see like this, if this is your data point, so there is homoscedasticity. But here there is what we call heteroscedasticity. Why? If you could see, it's here, it's quite few, but as you proceed further, it seems like it's becoming bigger and bigger and bigger and bigger. Okay? So please make sure to have homoscedasticity. Okay, so that's homoscedasticity. And the seventh assumption, it's just a repetition now, so there are no significant outliers. So how come I would like to emphasize this again? Why? If consider this data set, for example, if there's an outlier. If this outlier, by the way, this is what you call your line of best fit. If there is an outlier, for example, your R here is 0.4. But if you will remove this outlier, what have you noticed with the R? You see it increases. That's why the presence sometimes of significant outliers makes the relationship go down. But if you move some significant outliers, I mean, then expect that the relationship becomes more pronounced and that your R value has a tendency to have a higher absolute value. Now, there are many ways to interpret correlation coefficient, okay? So the magnitude of the Pearson correlation coefficient determines the strength of the correlation. Although there are no hard and fast rules for assigning strength of association to particular values, some general guidelines are provided by Cohen, 1988. So if your R value has, if the absolute value, take note, the absolute value, meaning positive or negative, okay? Positive or negative numbers, its absolute value is always positive. It's between 0.1 and 0.3, meaning the correlation is small. If it is between 0.3 and 0.5, meaning there is a medium or moderate correlation between the variables. And lastly, if the absolute value of your R is greater than 0.5, then there is a large or strong correlation. All right? Okay. So let's have an example. Okay. Mr. Yin would like to determine if there is a significant relationship between business motivation and self-efficacy, and both are interval data. After gathering interval data from 30 businessmen through random sampling, he tallied the results. Test the hypothesis at alpha equals 0.05. Okay. So for this particular problem, the research question could be, 1, is there a significant relationship between business motivation and self-efficacy? Okay. In your opinion, what do you think? Are they related? Motivation and self-efficacy. Motivation and confidence. Do you think there's positive, negative, or no relationship? In your opinion, please comment your answer in our chat. Motivation and confidence. Positive, negative, or no relationship? Okay, we have here positive. Okay. So many of you answered positive relationship. Let's check if that is correct. Okay. So your HO, there is no significant relationship between business motivation and self-efficacy. HA, there is a significant relationship between business motivation and self-efficacy. State 3, the significance level. Alpha equals 0.05. And the same for this one, we will use Pearson's R. The fifth one, you state your decision rule. If P is less than or equal to alpha, then reject HO and report HA. If P is greater than alpha, then do not reject HO and you have to report HO. Do we have any questions or clarifications so far? Ma'ams. Questions, clarifications? None? Okay, no. Okay, none. This time, let's go to your data. So, we have here our data. And if you could see, we have here business motivation and self-efficacy. Okay. So here, business motivation and self-efficacy are both scale data because they are both, in this case, they are both interval data. Okay. Now, and take note as well that if we are going to place here the data in SPSS in the data view, make sure that the data is paired. Okay. So it's understood that respondent number 1 has a business motivation score of 20 and his or her self-efficacy score is 21 and so on. This is actually paired data also, so make sure that your data is matched. That for every respondent, his business motivation is matched with his or her self-efficacy. Now, we might want to ask first, no? What do you think is the appearance of the graph? So, of the scatter plot. So for the scatter plot, let's have analyze. Go to graphs. After graphs, you go to chart builder. You click it. Okay. And just click OK. So you might be interested in doing this. Okay. So how do we do this? So for the meantime, we have here our x-axis and we have our y-axis. For business motivation, let's place it in the x-axis part. And for the self-efficacy, let's place it in the y-axis part. So you see, we have here the two now, business motivation and self-efficacy. And let us choose scatter plot, okay? And choose this one. It's just a simple scatter. And you may now click OK after that. And this is now how your scatter plot looks like. Now, take a look at that. Based on the scatter plot, do you think negative, positive, or no relationship? What do you think? Take a look. Do you see a line, a trend that's falling to the right? Do you see the line that, let's say, rises to the right? Or there's no line at all? What do you think? Take a look. Is it positive, negative, or no correlation? Okay, so many of you are quite shy. Now, it's okay. No? Negative, damo, or there are many outliers. Okay, let's see. So if we go back with our data, we could click analyze. To do Pearson's R, let's click analyze. You go to correlate. Okay, here. After analyze, go to correlate. And after correlate, you go to bivariate. No correlation daw, according to Ma'am Melissa. Okay, again, analyze, correlate, and bivariate. Then click it. Okay. And so with such, we can now highlight that if you wish, you could first click on this, then press the arrow, or you could simply have them both selected, then press the arrow head going to the variable section. And if you could see in the correlation coefficients, you can choose either Pearson, Kendall-Stowe, or Spearman. In our case, we will choose Pearson. Okay? And you may now click. If you have done this, you may now click OK. Okay. And this is now your correlation table. And I will go back. I copy this and place it here. Okay, so for a quick modification, so I just place here 30. Okay. Now, so here is the Pearson star table. So this is business motivation with, if you could see, if I correlate business motivation to business motivation, it's 1. Of course, you've correlated the data to itself. In a similar manner, if you correlate self-efficacy with itself, the Pearson correlation here is 1. Why? Because, of course, every time you correlate something to itself, of course, they would perfectly fit. That's why the answer is 1. However, that's why you can choose either business motivation to self-efficacy, and here is the value. So your R, your Pearson correlation, it's your R. And the sig two-tailed again is your P value. Okay? So how do we write the value? So we have R, you write R first. Inside the R, you write there the N. Take note, it depends again the university. It depends upon the school. It depends also upon the panel members, how they wish to have the results written. But for now, inside the R, I will place the N, the value of N. So R 30 equals, then this, no? This is your Pearson correlation, negative. This time, that if your answer is negative, then you really have to indicate the negative sign. That's why, but I round it to 2 decimal places. That's why it's negative 0.25, comma, P equals the sig two-tailed, which is 0.186. So 0.186 is greater than 0.05, right? So if it's greater than 0.05, if we go back, what does it say? If it's greater than 0.05, then do not reject HO and report HO. That's why it's, if you report HO, then there is no significant difference. So we could say there is no significant or a non-significant, comma, small. You might be asking, sir, where did you get small? Small is taken from, okay, take a look, huh? Your R is negative 0.25 approximately. Din siya ma-fall. Take a look at these coefficients. Where does the negative 0.25? The absolute value of negative 0.25 is positive 0.25. Where does it fall? Is it small, medium, moderate, large, or strong? Okay, if 0.25, its absolute value is the absolute value of negative 0.25 falls between 0.1 and 0.3, right? That's why I copied small. So there is a non-significant, comma, small, negative. Why negative? Because the sign here is negative. If the sign here is positive, you write positive, okay? Correlation between business motivation and self-efficacy, okay? Now, so here's our conclusion. Since P is greater than alpha, then do not reject HO and report HO. Thus, there is no significant relationship between business motivation and self. I just copied the HO, by the way. Thus, there is no significant relationship between business motivation and self-efficacy. This implies that business motivation and self-efficacy are not related. Okay? Now, so you may just write this. Thus, there is no significant relationship between business motivation and self-efficacy. This implies that business motivation and self-efficacy are not related at all. Meaning, wala sila relationship. Okay. Questions or clarifications about the first example? So that's how we do it if there is no significant relationship. Here? Okay, so may pamangkot. If there's questions, feel free to ask. All right. Now, let's have another example. Okay, here's the example. Mr. Yin would like to determine if there is a significant relationship between height in inches and weight in kilograms of his employees. After gathering interval data from 30 people through cluster sampling, and remember that cluster sampling is also probability sampling, he tallied the results. Test the hypothesis at alpha equals 0.05. So from this one, our problem could be are height and weight significantly related? You see, no? I stated the manner. I had a different manner of stating. But if you ask, is there a significant relationship between height and weight? That is also correct. Because the problems could also be stated differently by different researchers. And there is more than one way of stating the research problem. So my HO, height and weight are not significantly related. HA, height and weight are significantly related. Your alpha is still 0.05. Your test statistic is still Pearson's R, and the decision rule is still the same. Questions or clarifications before I proceed? No questions? Okay, thank you. Okay, so here we are back with our data, and we have here the column for height. The height here are all in inches, by the way. And we have here weight, okay, which are all in kilograms. So for example, take a look. For a person whose height is 65 inches, his weight is 60 kilograms and so on. And these are also all paired data. Okay. Now, let's check first the scatter plot now. So to do this, let's go to graphs, chart builder. And you could see the previous one that we had is still here. So just click it, click delete. You click self-efficacy, click also delete in your keypad, and replace, let's say the height can go here on the x-axis. Sorry. Let's have height in the x-axis. And let's have the weight on the y-axis. Take note, you could actually have them reversed, okay? But in some instances that there is an independent variable and a dependent variable, the independent variable is usually placed in the x-axis or the horizontal, and the y-axis, you place here the dependent variable, if there is really indeed a true independent and dependent variable. Now, from here, still scatter plot, then click OK. And this is how the scatter plot looks like. Okay, take a look. If there is a line there, take a look at the trend of the points. Is it more of positive? Is it more of negative? Or no relationship?
No relationship.
I think no relationship.
What do you think?
No relationship.
No relationship? Okay. No relationship. Let's see. Let's see what statistics says, no? So let's have analyze. You go to compare means. Then, sorry, you go to correlate. I'm sorry for that. Then you go with
By variance.
by variance.
Variance.
Yes. So let's select again the previous ones we had and return it them to the left side. And this time, we will now choose height and weight and place them both in the variable section. Make sure po that Pearson is checked. Okay? Make sure that Pearson is checked. And after which you could now click OK. All right. And this is now the table. That is the result of your statistics, of your SPSS. And I have it here. Okay, take a look. So how do we report this? That would be your R is this one, no? Approximately 0.59 when rounded to two decimal place. Your R, okay, is your P is 0.001. Is this significant or not significant? Your P is 0.001. It is significant or not?
No.
Oh.
No significant.
Your P is 0.001. Significant daw. Okay? And take note. Take a look at the Pearson correlation, 0.589. Is it small, moderate, or strong? If you could still remember.
Moderate.
0.589.
Large, ugly, 5.
It is. Let's see, balikan po natin. 0.589. O, anong sabi niya?
9.589. Okay, strong.
There is a strong, right? Large or
Yes,
strong
strong.
correlation. Because
Correlation.
0.589 is larger, its absolute value is larger than 0.5.
Mm.
That's why we could say large or strong correlation. That's why I place here, since P is less than alpha, no? Okay. So R is equal, R, inside R is 30, by the way. So you have here your results equals 0.59, comma, P equals 0.001. So P is less than alpha, and thus there is a significant. Why significant? Because P is less than alpha. Strong, where did we base the strong? Based on the scale we had earlier. Where did you base the positive? The sign of Pearson R. If the sign is not placed, it is already understood to be positive. Correlation between business motivation and self-efficacy. Again, there is a significant, strong, positive correlation between business motivation and self-efficacy. Since P is less than alpha, then we check HO and you have to report HA. So for our conclusions, I will go back to my given and copy the alternative hypothesis. And I may say, thus, height and weight are significantly related. Since the relationship between the two variables is positive, interpret what it. Take note, you can do this if the relationship is significant. Since the relationship between the two variables is positive, this means that in general, as height increases, weight also tends to increase or increases and vice versa. Moreover, the relationship between the two variables is, this is already, I don't know, strong, right? Is strong. Do we have any questions or clarifications before we proceed? Okay, thank you, Ma'am Piliado. That's actually correct. Okay. So with that ends the discussion on Pearson's R.
So again, why do companies have advertisements? So why do they spend too much on advertisement? Do you think that advertisements help companies improve their income? And if so, how? And maybe we could ask ourselves, have we been convinced by advertisements before? If that's the case also, how? Between income of companies and expenses on marketing ads, which of these two variables influences the other? That's a good thing, right? Because if a certain variable influences the other, then probably that independent variable could be used as a basis to predict another variable, which is your dependent variable. So this time, if we wanted to measure, or let's say, if we would like to determine predictors if a certain variable predicts the other, then we might be needing prediction analysis, no? Particularly the use of regression analysis. So maybe you would agree that expenses on marketing ads influence income of a certain company, right? The independent variables here, refers to factors that a certain researchers hypothesize to have an impact on the dependent variable. Whereas a dependent variable is the main factor that you're trying to understand or predict. So in this case, the expenses on marketing ads on the left is an independent variable and maybe could be used to determine if it really impacts income or not. So just remember the acronym DRY-MIX. So D stands for dependent variable, R is the responding variable, and it should be found on the y-axis or the vertical axis. Diba? For example, if for math majors, we have your x-axis and y-axis. The horizontal axis is the x-axis or your independent variable, whereas the vertical axis or the one that's standing up is your dependent variable. Whereas for the mix, M is the manipulated variable. It's your independent variable, and it is found at the x-axis or in the horizontal axis. So now, if you wish not only to determine the relationship of two variables, but if you would like to test further if that independent variable predicts another variable, then if we also satisfy all the conditions on the use of this test, then we may be using regression analysis. In this case, we will just use simple regression analysis. When we speak about regression analysis, it is a statistical approach for modeling the association between a dependent variable called response and one or more explanatory or independent variables. It could be used to determine the strength of predictors. That's why if it is really a predictor, then we have to determine, no? Take note, for you to do this, it's important to determine if your two variables are actually significantly related with one another. If there is a significant relationship between them, that's why you could use Pearson's R, then you could run further regression analysis if you have a true predictor variable. For example, what is the strength of the relationship between expenses in marketing ads and the income of the company? You could also tell, you could use all this also for forecasting an effect. How much additional income will I earn for each additional 10,000 pesos spent or marketing ad? Why can you forecast? Because the regression analysis, no, yields an equation. You can form a linear equation and could be used for prediction purposes and forecast a trend. For example, for January, here's the sales. For February, here's the sales. The third for March, the sales is this. So using the trend, probably we could predict what will be the income of the company in 6 months or even in the 6 months. So let's talk about simple linear regression. There are different types of linear regression. The first one is simple linear regression. You only have one predictor variable possible, one possible predictor variable. Whereas if you have multiple linear regression, then you could have two or more of them. A simple linear regression assesses the linear relationship between two continuous variables. So again, continuous variables. So both variables should be at least interval. to predict the value of a dependent variable based on the value of an independent variable. This is also known as bivariate linear regression, but the most popular is simply linear regression. The dependent variable is also referred to as the outcome, target, or criterion variable, and the independent variable is known as the predictor, explanatory, or regressor variable. Okay? So, we could use regression analysis in these instances. Ma'am Amy, Ma'am Amy Rose, please read.
Letter A, determine whether the linear regression between these two variables is statistically significant. B, determine how much of the variation in the dependent variable is explained by the independent variable. C, understand the direction and magnitude of any relationship. And D, predict values of the dependent variables based on the different values of the independent variable.
All right, thank you, ma'am. That's why what is beautiful with linear regression is that your model, by means of an equation, could be used for prediction purposes. For example, you could use this to predict lawyer salaries based on the number of years that they have practiced law. You could also determine how much of the variation in lawyer salaries can be attributed to the number of years they have practiced law. For example, you could predict the salary, but apart from that, no, when we say variation, like how many percent in the variation of salary could be attributed or is influenced by the number of years in service. For example, is your salary affected by the years of service by 10%, 20%? How many percent of your salary is predicted by your years in service, for example? You could also use linear regression to predict the distance women can run in 30 minutes based on their VO2 max, which is a measurable fitness. Again, you could determine how much of the variations of distance run could be attributed to women's VO2 max scores as well. That's why if it is indeed, if one variable is really a predictor, that's why you could have an estimate of the possible value of another variable based on the value of the independent variable. Now, here are some of the basic requirements. Okay, so here are some of the requirements. The first one is you have one dependent variable that is measured at the continuous level. You have one independent variable that consists of two or more categorical independent groups. So pwede na ang yung predictor variable, your independent variable could be this one, no? Sorry. This is one way ANOVA. Give me a second. So for ANOVA, you have one dependent variable that is measured at the continuous level. You have one independent variable that is consists of two or more categorical independent groups. Of course, there should be a linear relationship between the dependent and independent variable as well. You should have independence of observations, as also mentioned yesterday. So the data of one does not influence the data of others. There should be no significant outliers as well. Your data also needs to show homoscedasticity. Okay, I mentioned that also earlier. There's uniform variance. Okay, indicates that the variance of the errors or residuals is constant across all values of your independent variable. You need also to check that the residuals or errors of the regression line are approximately normally distributed. And for your null and alternative hypothesis, for simple linear regression is your null hypothesis, the coefficient of the slope equals 0. And for your alternative hypothesis, you could say the coefficient of the slope does not equal 0. Okay. Or in the major, depending on your results, you can then state whether to reject or fail to reject the null hypothesis and whether to reject or accept the alternative hypothesis. But normally we use the term reject or not reject. Okay. And take note, in many studies involving linear regression, you could also say, for example, number of years in service is not a significant predictor of salary. That could be your null hypothesis. Or you could also say that number of years of service is a significant predictor of salary. That could be your alternative hypothesis. So a simple linear regression could be used to determine the change in the dependent variable for a 1-unit change in the independent variable. Determine how much of the variation in the dependent variable is explained by the independent variable and predict new values for the dependent variable given the independent variable. And this is what is beautiful with linear regression. For example, you may, for the first study design where you could implement it, you could say, determine the change in the dependent variable for 1-unit change in the independent variable. You may be able to state that exam scores increase by 0.42 of a mark of out of 100 for extra hour of time spent revising. Example lang na. Okay? That's why for every change, for every 1 hour change in time, 0.42 will be added to the marks of a certain individual on the test. So you see, this is change in the dependent variable. The second one, predict new values for the dependent variable. For example, you might have last year students' midterm and final exam results for a biomechanics course. Using this data, you construct a linear regression equation. When this year's class hits the midterm biomechanics exam, you use the linear regression equation to predict their performance in the final exam based on the midterm exam. Okay, that's why you could use this for prediction. Ma-predict mo. Given ang midterm score nila, you can predict the final exam score. But again, provided that indeed predictor gid man si midterm score, sang final term score. For the third one, determine how much of the variation in the dependent variable is explained by the independent variable. Example, how much does the amount of time spent exercising explain cholesterol concentration, a fat in the blood linked to the heart disease? Okay. So I hope it's clear, no? Pila ka percent? Pila ka percent sa exercise ang makapredict or magamit mo to predict the variance sa cholesterol concentration. So for example, okay, let's talk about identify the dependent variable and the independent variable x in the following pairs of variable, then explain your answer. Okay, let's have number 1. Let's say age of a cell phone and its price value. Which among the two is the independent variable and what is the dependent variable? Anyone? what affects the other variable? Okay, according to Ma'am Abigail, the IB or the independent variable is age of a cell phone, and price value is the what they call this? Is the dependent variable. I agree. The independent variable should be age of a cell phone, and the dependent variable is price value, because it is the age of the cell phone that predicts the price. Why? If the phone is new, I think the price is somehow higher. But if the phone is very old, it's old, no? And it's assumed probably by others that it's not functioning well compared to when it is new. So maybe they would buy it at a smaller price. So it's the age of a phone that determines its price. How about the second one? What do you think, Ma'am Christine? Ma'am Christine Bado, what do you think? Number 2, the amount of food a person eats and the person's weight. Or anyone? IB daw is the amount of food, and DB is a person's weight, and I agree with that as well. Okay? So you can continue this activity if you wish, but I hope what's important is that you know what is the independent and what is the dependent. Because later on, when we have our data, the independent variable will be placed on the x-axis or horizontal axis, and the dependent variable will be placed on the y-axis part. No? Now, if we consider the scatter plot below, you could see that the trend of the points is rising upward, or it rises to the right. And you could see that they are all not contained in one line, but there is that line there in red, shown in red, and known actually as the line of best fit or the regression line. Do all the points fall on the line? And the answer is no. But if the average vertical distances of the points from this line is the least, then we call this line as the regression line. And the regression line is, if you are a math major, now you know that this is what we call the slope-intercept form of a line, which is y equals mx plus b. Where, in this case, y is the dependent variable, x is the independent variable, m is the slope of a line, and b is the y-intercept of your line. Here, slope and y-intercept. So I believe math majors know about this, but for non-math majors, I believe, I hope that you could catch up with us, okay? Now, the slope, m, reflects how large or small the change in y will be for a unit change in x. Meaning, if your m or slope is positive, then for every increase of 1 unit sa independent variable natin, there will be a corresponding increase by the value of the slope on the value of y. And vice versa. If your m decreased by 1 unit, then the value of y will also decrease by the value of your slope. That's why, in this case, if the value of your slope is negative or m is less than 0, for every unit decrease sa independent variable, the dependent variable will increase. Baliktad sila. That's why you have a negative relationship. If positive relationship, plus plus, or minus minus. But if you have a negative relationship, one is plus, the other is minus. Or if the first is minus, the other will be plus. For example, if y equals 2x plus 1, you could see that m here is equal to 2. This means that for every unit increase in x, there is an increase of 2 units or of your slope. Okay? Pero kung nag-negative 2 na, if y is equal to negative 2x, it means for every increase, again, if it is negative 2, y equals negative 2x plus 1. For every unit increase in x, y will decrease by 2 units. So careful. The y-intercept B is the point at which the regression line will intersect the y-axis, of course. So to solve for B, just let x be equal to 0. It is also the value of y when x is 0. For example, if y equals to x plus 1, if x is 0, 2 times 0 plus 1, again here, y equals 2 times 0 plus 1. 2 times 0 is 0. 0 plus 1, 1. That's why B is 1. That is, if x is 0, then the value of y is 1. Okay, sige be? I'll give you an example. Show me or give a short interpretation of this. In this case, X represents the number of customers entering the store. Y is the income of the store. Okay. What does this mean? For every 1 unit increase, How about this? So you could see for every customer that enters, or you could say for every customer that for every increase of 1 customer, pwede man, a store earns an average increase of 11 pesos in its income. Like this, kung ano yung slope, yan yung additional income niya for every 1 customer that enters. If no customer enters, meaning your X is 0. Kung walang customer na nag-enter, the store earns 50 pesos. Maybe from other sources of income, aside from selling to customers. Okay? Now, try this. Just make a parallel statement. Okay. 10x minus 10. For every customer that enters, your slope is 10, right? Yes, yes. For every customer that enters, a store earns an average increase of what? How many pesos?
10 pesos.
Exactly.
10.
In its income. If no customer enters, meaning X is 0, so 10 times 0, that's 0, minus 10, it's negative 10. If no customer enters, the store earns a deficit of 10 pesos Maybe because it still has to pay other expenses like electricity, etc. No? That's what is meant if you have these equations, these regression equations. Okay. Now, let's perform regression analysis. No? So let's have this format for the set of data and perform the results. This is just our example. The following data shows the number of absences of 10 students in statistics class and their corresponding grade in the subject. Determine of the number of absences of students is a predictor of their final grade in math. So here, for your take note, now, here's a statement about the hypothesis. That could be what? What could be your hypothesis? The number of absences of students is not a predictor of their final grade in math. Whereas your alternative hypothesis, the number of absences of students is a predictor of their final grade in math. So your dependent variable here is the final grade in math. Your independent variable is the number of absences of students. So later on sa x-axis, muna ang number of absences. And for the dependent, that will be for the final grade in the y-axis. For the statistical test used, we will use simple linear regression. And for example, this is our output, no? Let me introduce to you what does this output mean? Because this one is used, is accomplished using Excel, okay? But also, I'm not really sure if other versions of Excel can do this. So it depends if you are able to install that to your laptop, no? So let's interpret the results. So there is a strong negative relationship between the number of absences in class and grade with R equals 0.89. Okay. So you might be asking, sir, bakit ganito yung itsura niya? Positive to, di ba? Bakit sabi niya negative?
Strong negative.
Actually, this is absolute value, no? If you are going to multiple R, is actually absolute value. But if you will run or use SPSS, it will show you that your R is actually negative. So here is the intercept, and this is your, take a look at the coefficients part of the Excel. The number of absences is the independent variable, right? So this is negative 1.40. This is now your A, or your M, or your slope. Depende. Some books use A, some books use M. But if some, you could use here M. No? And your intercept is 91.58. Your test statistic, your T statistic is that one, 156.72. Furthermore, this relationship can be modeled by the equation y equals, that's why here it's negative. Negative 1.40x plus the B here, which is 91.58. This implies, based on what we mentioned earlier, that for every day that a student is absent in class, there is an average decrease of 1.40 points in the grade in math. Why decrease? Because of the negative slope. If it's negative here, so dapat your multiplier here, that's why here it's actually negative also here. But this one kasi is absolute value eh. That's why hindi mo makita ang negative. This implies that for every day a student is absent in class, there is an average decrease of 1.40 points in the grade in math. In addition, if a student is never absent in class, he or she will get an average grade of, in this equation, no? Substitute x by 0, and you will get 91.58 or approximately 92 in math. Kasi rounded siya. Furthermore, the coefficient of determination r squared, ito po yung r squared. To get r squared, you just square the 0.89. That's why 0.89 times 0.89 gives 0.79, indicates that 79% of the variance in the grade can be predicted by the number of absences in the class. Meaning to say, kung ano man yung grade niya dyan, 79% of that, pwede palang ma-predict ng number of absences mo. The remaining 21% of the variation, di ba 100% yan? 100% minus 79% is 21%. That remaining 21% of the variation in the grade can be explained by other factors other than absences. Malay mo, those other factors could be, let's say, allowance, socioeconomic status. Ano kaya, no? Basta may ibang factors na hindi niya consider siguro, no, na maaari naka-affect sa grade sa math. Halimbawa, motivation, dedication, and so on. This equation or model, y equals negative 1.40x plus 91.58, significantly fits the given data with significance f equals 0.000. Here, if this is less than 0.05, therefore significant. Could significantly fit. Pero kapag na-greater than sa 0.05, parang hindi masyado. Okay? So, to do this in Excel, but again, depends po sa Excel na ginagamit mo. What's the slope? What's the slope here? The slope here is
1.40.
positive or should we include negative or not?
Negative 140. 1.40, sir.
Negative, sir.
Tama. What's the y-intercept?
Y-intercept.
Ang slope, negative 1.40. Ang y-intercept, siya yung walang kasamang variable. So the y-intercept is?
90.58.
90.58.
Tama. What does it indicate? If x is 0, meaning
She will get
90.58 na grade, no? Or, pero sa card natin kasi, nira-round off yan eh.
So,
Magiging
91.
Magiging 91 ang predicted grade.
21 siya.
Tama. What's the predicted grade of a student who has 3 absences in class? Ang absences, X or Y? What
X,
is the
sir.
X yan? So to do that, if you have your calculator with you, isli ang X or palitan ng X ng 3. Then solve. Use your calculator. So we have negative 1.40 times 3 plus 90.58. And you will get, ano po nakuha ninyo? $86 something. I got 86 something.
86.38, sir.
Tama.
86.
Did you get 86.38?
Yes, sir.
Yes, sir.
Yes.
Sure.
So yan,
Wala
So
ko
yan
siya nakuha.
So yan, ano ma'am, negative ba? Don't worry ha, may negative pa ha.
Okay.
Negative 1.40 times 3 plus 90.58.
Okay.
So the predicted grade of that student will be 86.38. Pero sabi niya, at sino ka upang sabihing 86.38 yung grade niya? Diyos ka ba? O di ba? Parang drama na. It's not like that, no? Take note. The prediction is not perfect. It doesn't mean na amugin na yung actual grade niya. This is the predicted grade, but it's possible that this will not be the actual grade. Because remember, prediction models are not perfect. Okay? So may mga flaws man na siya, and it cannot really predict everything with 100% certainty. Questions? So hindi na siya perfect ang model ha, tandaan natin nila. But this, okay, is a good, but this could be used for prediction even though it's not perfect. Okay, so to do this, no, depende sa type of Excel that you have. I sent to you the Excel file there. You could go to data analysis under the data tab. However, when I try it sa akon, ang akong Excel doesn't have this. That's why I cannot do these steps. No? But if you have it in your file, if you have it in your, what do you call this? In your Excel, so you could click on data analysis. And the steps are true for MS Excel 2007. Okay. So you click data tab in the menu bar. So data here. After you click that, you can go to data analysis here sa pinaka right. In my case, however, I tried doing this. I was not able to get the screen because most likely I was not able to probably encode, no? Or I mean, to have the statistics, the data analysis like this installed in my laptop. So it depends again, huh? Okay, so you have this. This will pop out. Then you can choose regression. So don't worry, I'll be giving you the video of this presentation later. You go to regression. In the regression dialog box like this, you click this thing, the input Y range, and drag it down to B11 and press enter. When we say drag down, you highlight going down like this. So this is drag down like this. Okay. So it's assumed that you will do it all by yourself. And in the regression dialog, of course, for the X range, you will all do also the same thing. Y range is the dependent variable. X range is the independent variable. You tick labels since the column labels are part of the range chosen for X and Y. Do not tick this if column labels are not part of the range. Choose output range in the output options here. Click this and choose a cell in the sheet where you want the result to appear. In this case, A15 is chosen. Cell A15, no? Column A, row 15. That's what is meant when we say A15. Then click OK. And you will have these results. That's how you got those results. No? Like this. And of course, the interpretation of this is similar to what we did earlier. So the multiple R is the absolute value of the correlation coefficient of two variables. Be careful, ha? If this is negative here, it's understood that multiple R is also negative. There's negative relationship. But if the value here is positive, your slope, then it's understood that your multiple R is actually positive. No? Now, R square is what we call the coefficient of determination. So you could achieve this by, if you have the multiple r, just multiply the multiple r to itself, or you square the number, you will get r squared. No? And it is the proportion of the variance in the dependent variable that is explained by the independent variable. If r squared is 0, then y cannot be predicted from x. If r squared equals 1, then y can be predicted from x without error. This is perfect prediction, r squared equals 1. If r squared equals 0.10, meaning 10% of the variance in the dependent variable could be predicted by the independent variable. If it's 0.20, 20% of the variance in the dependent could be predicted by the independent, and so on. Take note, that r squared ranges only from 0 to 1. And it is impossible to get a negative value for r squared. If we talk about the significance f there, it gives you the probability that the entire model as a whole is wrong. The p-values here in the dalom, in the bottom part, indicates the probability here that the estimated coefficients is wrong or unreliable. If the value of the p is less than 0.05, then these can significantly predict. However, if at least one of them is greater than 0.05, then either the intercept or absence cannot predict your dependent variable, which is grade. That's why, take note, if the value here is less than 0.05, here, it's less, this p-value for intercept is less than 0.05. So we could use the intercept for prediction purposes. We can also see that the p-value for absences, 0.0019 4978, is less than 0.05. That's why we can also use the absences, the slope for absences, for prediction purposes. So also, it can be seen, I think this one was mentioned earlier. It can be seen from the result that the number of absences in grade has a strong negative relationship with r equals negative 0.92. You might be asking, sir, what's the basis of strong? The basis is this. Go back here to your Pearson R. Here. 0.916 something has an absolute value which is greater than 0.5. That's why it is strong. The slope value or the value of m equals negative 1.47, which is significant because it's less than, because it's 0.000. Add another 0, please. Another 0. It indicates that there is an average decrease of 1.47 points in the grade in statistics for every day that a student is absent in class. Why do you say so? If it is positive here, increase. If it is negative here, decrease. The y-intercept of the value of p is 91. It indicates with p equals 0.000 approximately, rounded to 3 decimal places. It indicates that if a student has no absence in class, then a student can get a grade of 91 in statistics class. Furthermore, the coefficient of determination, here, your r squared, equals it should be what? Coefficient of determination is, it's not 0.92. Round this to two decimal places. It's 0.84, right? 0.84. That's why it should be 0.84. not 0.92. That's why, no? So we have seen an error. Therefore, the coefficient of determination R squared equals 0.84 indicates that around 84% of the variance in the grade can be predicted by the number of absences in class. So how come it's 16%? Anyone? Where did the 16% come from? What happened? Anyone?
100% minus 84%, sir.
Very good. Correct. Thank you, ma'am. So 100% minus 84% is 16%. That's why the remaining 16% in the variation in the grade can be explained by other factors other than absences in class. This equation or model y equals negative 1.47x plus 91 significantly fits the given data with significance f equals 0.000. Here. Let's round it to the decimal places. Questions or clarifications? None?
None, sir.
Okay. So, I would like you to indicate the following. Okay. Take a look at this. Your independent variable is expenses on PB ad. Your dependent variable is income. Okay. What is R here?
$0.88.
Very good. It's here. Should it be positive? Should we write positive 0.88 or negative?
Positive.
Very good. Kaya nga,
Positive
how come?
0.88.
How come positive? Because the coefficients here for the TV ad spend is positive, so it's understood to be 0.88. What about R squared?
Mm. 0.77.
Very good. 0.77. What is our equation? Din rin gamiton natin? We will use the coefficients here.
Coefficients.
So what is our equation? Y equals what?
Y equals to
R squared is 0.77, sir.
Yeah, R squared is 0.77. But how about for letter C? The equation in the Y equals mx plus b format. You will be using the coefficients here. What's the equation?
Y equals 17.73 plus 428 point.
Ang x, anong iupod sa x? Ang 17.73 or ang 428.78? Ang intercept, that's the y-intercept, ha? And remember, ang y-intercept, wala ginaupod sa x.
okay.
Sir.
So Y
7
plus
equals to
Diin ko ibutang si x. Upod siya ni 17.73 or together with 428.78. It is upod ni
7.
ni 17.73.
17.73.
Yes, that's why the correct answer for letter C is y equals 17.73x plus 428.78. It's there in our chat. Please check. Okay. Okay, thank you. Correct, Ma'am Pilyado. Tama. Okay? I hope it's clear. Now, let's use SPSS to do this. No? So, for example, studies show that exercising can help. Okay. Now, this time, how do we know? No? Let's skip some of these slides. How do we know, or how do we do linear regression analysis in SPSS? Okay, to do this, I have with me my data here. Okay, so in the variable, I think I use the same data. In the variable view, number of absences is scale. Because why? Number of absences is ratio data. Grade is also ratio data. Grade is also a scale. No? And here are the number of absences of each student. And here are their grades, no? Corresponding grades as well. So the thing is, how do we do simple linear regression in SPSS? Now, let's take note, before we proceed with simple linear regression, it is an important assumption to check if there is a significant relationship between number of absences and grade. So again, how do we ascertain if number of absences is related to grade? What parametric statistical tool can we use? To determine relationship.
Pearson product.
Tama. We will use Pearson's R. That's why hindi tayo mag-Pearson kung may significant relationship sila or wala. Let's click analyze. Go. But before to do with Pearson, check tabi ang graph, anay.
Graphs.
Let's check first that plot. So we have to graph. We go to chart builder. And let's choose scatter for that. This one. So we will have number of absences to be here. Sorry, wait na. Let's click this one. What do you think is the independent variable between the two? What is the independent variable? Number of absences or grade?
Number.
Independent.
Independent. X. Grade.
Which affects the other? Does your absence affect your grade, or your grade affects your number of absences? Which is which?
Absences, sir.
Tama. More or less, no? Literature would support that number of absences affects grade. So, anong ibutan ko sa x-axis? Number of absences or grade?
Absences.
Number of absences.
Number of absences.
Absences.
Because that's your independent variable.
Yes.
The grade is your dependent variable that we place in the y-axis. And with that, you may now click OK. O, take a look at the data. Take a look at the points. Related sila, ihan. Is there like a line?
Yes.
Tama, no?
Yes, sir.
Is the line,
sir.
Yes, sir. Related.
does it appear to be rising or falling to the right?
Rising.
Right?
Pakadto, so from left to right. Ga-rise or ga-fall? Tanawan yung points.
Ga-fall, sir.
Ga-fall sa right. Kung ga-fall siya sa right,
Mm-hmm.
are you expecting your slope to be positive or negative?
Right shall use positive.
Again, Ang value duga falls sa right. So are you expecting the slope to be positive or negative?
Upadto sa right.
Yes.
Gahulog sa right.
Yes.
Positive or negative?
Kagahulog. Imo yung ba? Kapat yan.
So it would be,
Positive, sir.
ano?
Positive.
Gahulog sa right. Again, it's either pasaka or panaog. From left to right. Tanawan nyo. Amo ni siya, oh. Kung halin sa left pa right, nga panaog, negative na ang slope.
Ah, okay.
Pero kung halin sa left, pakadto sa right, nagapasaka, positive na ang slope.
Ah,
So are you expecting negative or positive relationship here? Negative, tama?
negative.
So therefore, I'm expecting nga negative ang slope dire. I'm also expecting nga negative ang value ni R dire. But again, check ta kung significantly related din man pala sila or hindi. So to do this, sige be, Pearson sa kita anay, go to analyze,
Analyze.
then
Then
correlate, then by
I
variate. Then highlight the two, place them in the variables, and take note, make sure that Pearson is checked. Dapat naka-check na lahat. It's checked by default. And if you are done with this, click OK. And it will look like this. Tanawan nyo. As expected, negative 0.888. Sakto?
yes, sir.
So, and then ang munang results niya. Be, tanong ko pares ng sabat. Wala siya ka ano. It's not included here, but it's okay, no? So sige. So anyway, let's interpret this one. Is this significant or not? By the way, there is a negative relationship because the value of R here is negative. Is this small, moderate, or strong?
Strong.
Strong. Because this one has an absolute value that's greater than 0.5. Is this significant or not? Significant or not significant? Take a look at the sig2-tailed or the p-value. It's 0.000. Significant or not?
Not significant.
Anyone? Is it significant or not significant? When siya significant gani?
Not significant, sir.
Significant, sir.
Significant.
Significant.
How come? How come significant? Because
Less than the sig-tailed is less than 0.05.
Yes.
That's why,
less
ha?
than.
That's why.
Less than, yes, sir.
Kung less than sa 0.05 or our alpha for our class, then it's significant. But if it is greater than 0.05, then it is not significant.
Not significant.
So in this case, there is a significant negative relationship between number of absences and grades. So again, clarification. Is number of absences related with grades, Tere? Yes or no? So, related sila o hindi?
Related, sir.
Related. Because related sila and significant, in fact, because the p-value is less than 0.000. Kung na-greater, sorry, 0.05 I mean, since less than siya sa 0.05. However, kung ang nakuha mo nga p-value is greater than 0.05, meaning hindi sila related significantly. That's why it's important for you to run your regression analysis, dapat significantly related sila anay. Again, remember this. One of the assumptions of the use of linear regression analysis is that there is a significant relationship between your independent and dependent variables. Okay? So, since that mas significantly related sila, then now we can proceed with the next step. That is, we can now perform linear regression analysis in SPSS. Take note kung hindi sila significantly related, or if the computed p-value is greater than 0.05, then you should not proceed to linear regression. Ika less than 0.05, pwede kita proceed. Okay. So let's go back to our data. To perform linear regression, simple linear regression analysis, go to Analyze. Go to Regression. And after that, go to Linear. Okay, so again, here's a step. Analyze, Regression, Linear. Then click it. Okay. Diin ko ibutang si number of absences. Independent or dependent? Number of absences is?
Independent, sir.
Independent. Grade is?
Dependent.
Dependent. Tama. Diba? Amotong dependent. That's why it's under take note Careful, Gid. Dapat sakto pagbutang mo. Balaan mo kung sino si independent. Balaan mo kung sino ang dependent. Then you could click. If you wish, you could click plots. Histogram, if you wish a normal probability plot, it's up to you if you wish to have that. Statistics also, you could press this. Estimates, R-squared change. If you wish to have descriptives, you could click that. Descriptives, that's your mean, median, mode, for example. If you wish to state a confidence interval, check lang which one you would like to have. No? Let's say, Durbin-Watson. Magusto ko lang covariance matrix, and so on. Then click continue and click OK. Okay. So now, here, for example, for your descriptive statistics, we have the following. The mean of your statistics, in this case, it just gave you the mean and standard deviation. No? Mean grade is 86.66. The average number of absences is 3.53. With their standard deviations, and your n equals 32. N equals 32 tells us that there are 32 respondents, no, in this case. So you could see also from here, remember we ran Pearson R earlier? It gave you the same answers here. Okay? And so in this case, so the variables entered, number of absences. This is your independent variable. And so you see, your R here is 0.888. Here, it's negative 0.1, it's negative 0.888. But again, that's why in the model summary part, it just gets the absolute value. Positive man na siya or negative, it just places the positive value. That's why always go back, always go back to your Pearson correlation, or go to the bottom. For example, here, take a look at the coefficients, look at the unstandardized coefficients, look at the beta of the unstandardized coefficients. So you see it's negative here, the slope for the number of absences. This is your slope, the negative 1.396. And the constant is your y-intercept, 91.585. If you see that the number of if the slope is negative, it also implies that r here is negative. Careful. Your r squared, if you square this, will be 0.788. Okay. And if you have your r squared change, you see, since you only have one variable to use to enter, whatever r squared is, the same as the r squared change. Okay. It will have a different case later on if you have multiple linear regression. But let's have simple linear regression lang for today. And what else? So this is your F for your ANOVA. You see it's significant. The sig2 the sig here is significant because it's less than 0.000, meaning to say the model later on that you could derive can has a good fit to your data. And for your coefficients, take note ha, use the unstandardized beta coefficients. Okay. So if X is the number of absences and Y is the grade, using these coefficients, what is your prediction equation? This type in our GC. Use this, huh? Y equals what? Okay, I'll give you a minute to type your answer. Do not round lang, anay, ah. Just use the what the values you see there. Okay, according to Ma'am Abigail, y equals negative 1.396. Ma'am, may kulang. Ma'am Abigail, may kulang, no? Di mo ibutang si x. Upod ni 139 ni negative 1.396 or upod ni 91.505. Okay, according to Ma'am Pilyado, y equals negative 1.396x plus 91.585, and I agree with that also. So don't forget ang x, ha? Yes. So thank you, Ma'am Pilyado, no? But thank you also, Ma'am Abigail. Y equals negative 1.396x plus ang constant amo ng y-intercept plus 91.585. And take note, how much of the variance, focus here, how much of the variance can be attributed to your independent variable? So dili, no? Focus ka sa r squared. This is approximately pila ka percent gani? 0.788. This is 78.8%. So rounded to the nearest whole number, that's 79%, which means 79% of the variance in the grade, which is your dependent variable, is dependent on the x or your absences. So again, 79% of the variance in the grades could be attributed to the number of absences. Pila ka percent ang hindi pwede ma-attribute sa variance? Kay 79% from absences. 21%. Exactly. So the 21% of the variance in the grades could be attributed to other factors. Okay, thank you. I hope it's clear. Now, So that's why you could use, no? So for your write-ups, for example, this is just an example write-up for the cholesterol. So a scatter plot of cholesterol concentration against average daily time spent watching was plotted. Visual inspection of the scatter plot indicated a linear relationship. This is for the scatter plot, no? Then you could also report, no? So this was the procedure, but this one was done for the cholesterol. But don't worry, I have exhibited that in the SPSS just a while ago, no? So a large part of the rationale for testing independence of observations is based on your study design. Indeed, you may have a study design where it is highly unlikely that observations will be related. And for this reason, you will not need to test for independence of observations statistically using the Durbin-Watson test. That's why we will not do that anymore. But if ever you would like to make sense of the Durbin-Watson, it says here, for example, if the Durbin-Watson coefficient is 1.957, the Durbin-Watson statistics can range from 0 to 4. You are looking for a value of approximately 2. Take note of approximately 2, which indicates that there is no correlation between residuals. You can see that our value is very close to 2. In this case, 1.957. So it can be accepted that there is independence of errors or residuals, and that you could report it in this manner. Okay? So, but again, no, there are some instances that outliers would occur like this. That's why looking at the data alone, no, by visual inspection, you might see that some data might be off. So we can detect outliers visually using a scatter plot, just like what we did earlier. So you have an option to, if you wish to have better or higher R values that are higher, you might wish to remove an outlier, for example. But if you wish to include an outlier in your analysis, then expect that the value of R will have an absolute value that is less than the moment you remove, no? When compared to the results when you remove the outlier. So if you do not want to remove an outlier or feel you cannot, you have 3 choices how to proceed. You can, number 1, transform the dependent variable. So data transformation, we have many of them: logarithmic, size reduction. There are many. Run the linear regression with and without the outlier. So try, no? Like, compare mo ang results with ito with outlier, ito without outlier. And if there is no appreciable difference in the results, meaning to say, if the results with and without the outlier are similar, or they are not really far from one another, then you may choose to keep the outlier. Or run a regression with robust standard errors. Okay? Now, testing for homoscedasticity. The assumption of homoscedasticity is an important assumption of linear regression and indicates that the variance of the errors or residuals is constant across all the values of the independent variable. Due to the manner in which the residuals acts as the errors, this assumption of equal error variances can be checked by inspection of a plot of the unstandardized or standardized residuals against the predicted. The previous procedure you ran will have generated the following plot using the standardized residuals. So if there is homoscedasticity, the residual or errors of prediction will be equal across the standardized predicted. or that is your fitted values. This will mean that the points of the plot above will exhibit no pattern and will be approximately constantly spread. That is, the regression standardized residual scores on the y-axis across the fitted values. However, if your residuals are not evenly spread, meaning may pattern siya, no? Nga iban, for example, they differ in height, but for example, they show a funnel shape. You do not have homoskedasticity. Instead, you have what is called heteroskedasticity. And for example, like this, you have an increasing funnel, like this one. As you go from left to right, the height is increasing. That's increasing funnel. You also have from left to right, the height becomes smaller. That's a decreasing funnel. Or if you have a fan shape like this, increase, increase, decrease, 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 increase, then your data does not exhibit homoskedasticity. These are examples of heteroskedasticity. So you may report if there is homoskedasticity by visual inspection in this manner. You could say there was homoskedasticity as assessed by visual inspection of a plot of standardized residuals versus standardized predicted values. Okay. Also, no, in our case, you could check your histogram if they exhibit or resemble a normal curve. The mean and standard deviation should have values of approximately 0 and 1 respectively for your p-plot. Also, for your p-plot, although the points are not aligned perfectly along the diagonal line, so if this is your diagonal line, although this is not perfect nga makita dira, they are close enough to indicate that the residuals are approximately normally distributed. That's why dapat mas manami tanigid if the residuals are, even though they don't lie on the line perfectly, but at least they are close to the line. As linear regression analysis is fairly robust against deviations of normality, from normality I mean, you can accept this result as meaning that no transformations or otherwise need to take place. You have not violated the assumption of normality as well. Also, notice how much clearer it is to assess normality using normal probabilities plots rather than histograms. No? Demonstrations of what different types of non-normality look like on a normal probability plot are shown below. So you see, this is an example of positive skewness. Remember, I mentioned last time, for positive skewness, the majority of the data set are low. The numbers there are quite lower than the sum. And for negative skewness or negatively skewed data, majority are higher compared to, and there are only few who got low. So you could report residuals were normally distributed as assessed by visual inspection of a normal probability plot. Now, to interpret results, may I ask you to read, Ma'am Abigail? Please read. Okay, I'm not sure. Ma'am Abigail, are you with us? Is she available? May I ask you instead, Ma'am Rhea Jane Piliano? Please read. Ay, ma'am, hello. Batian nyo si ma'am? Sa akon daw hinay, madaw buron. I'm not sure. Madaw,
Hinay, sir.
Oo.
Wala, sir.
Okay. So, sino ang pwede ka volunteer na lang? But thank you, ma'am, ha? Oh, siguro sa signal, siguro. Any volunteer? Can we have you, okay. Sige, ma'am, Ma'am Amy, the line. Thank you.
First, you need to determine whether the linear regression model is a good fit for the data. There are a number of statistics you can use to determine whether the linear regression model is a good fit for the data. These are A, the percentage of variance explained, B, the statistical significance of the overall model, and C, the precision of the predictions from the regression model. Therefore, on page 16, we take you through the model summary and ANOVA tables, which contain all the information to evaluate A and B, while C is addressed in the third bullet below. Second, you need to understand the coefficients of the regression model. Now that you have interpreted the overall model fit, you can interpret and report the coefficients of the regression model on page 17. These coefficients are useful in order to understand whether there is linear relationship between the two variables. In addition, you can use this regression equation to calculate predicted values of cholesterol concentration of given values of average daily time spent watching TV. Third, you can use SPSS or statistics to make predictions of the dependent variable based on the values of the independent variable. For example, you can use the regression equation from the previous section to predict cholesterol in concentration for different average daily time watching TV. Example, cholesterol concentration for an average of 160 minutes of TV per day. On page 18, we show the procedure in SPSS statistics to make predictions of the dependent variable based on different values of the independent variable, as well as explaining how to interpret these results.
Okay, thank you. That's why I was able to show this once earlier, no? On how you could interpret the results. Okay, we have this one also earlier. I also explained your R squared. Normally, we do report usually the R squared only. But for the adjusted R squared, it is the percentage of variation explained by the model in the population. The adjusted R squared corrects the positive bias to provide a value that would be expected in the population. The adjusted R squared value, which is in yellow there, is an estimate of R squared in the population. Take note, the R squared that you have here is understood, no, to be from the sample, but assuming nga butanta sa population mo na siya ginkuha, ang pwede, it's 0.120 na siya ang R squared. Nag-adjust niya. Adjusted R squared is also an estimate of the effect size, which at 12% is indicative of a medium-sized effect according to Cohen's classification. So, siya, okay. So here are some of the values earlier, no? We also had your ANOVA, which I explained yesterday, your DF, and the other numbers as well. And I also made use, no, earlier, I also taught you how to make the regression line. And take note of this, ha? Take a look at the sig of the constant. 0.575. That's the P value there. Is that significant or not significant? This one. Ang sig or P values ang constant. 0.575. It's greater than.
Not significant, sir.
So not significant siya. Right? So what does this mean? The intercept is not usually of much interest. It is the value of the dependent variable when the independent variable is 0. That's why amo na siya, no? Ang imong y-intercept. As such, if the independent variable is 0, then the intercept is estimating the mean cholesterol concentration when a certain independent variable is 0. Okay? Now, however, this intercept is not statistically significant because it's greater than 0.05. You can see that the intercept is not statistically significant, meaning that it's not different from 0, because this one is close to 0. Again, this is of little interest. Much more importantly and of much greater interest is the slope coefficient of your independent variable. No? So since nami siya kay nga significant siya eh. Take note ha, if it is significant, then it will be part of your equation. No? But if it is not significant, then usually you do not really place that. There are instances, no, that you don't place it as part of your equation. Take note, they have to be significantly related first. After establishing that they are related, you have to establish if it is a predictor or not a predictor. So may instance na related sila, pero hindi siya predictor. May instance man na related sila and predictor man siya at the same time. So again, before you determine if it is a predictor or not, you should make sure that they are related significantly. Okay. Remembering that the slope of the coefficient represents the change in the dependent variable, no? You can see here that for every unit increase, in time in minutes spent watching TV, there is a corresponding increase of 0.037 in the cholesterol. Okay. Now, you can see that the p-value for time in minutes spent watching TV is less than 0.05, which means the slope coefficient is statistically significant. If p is greater than 0.05, you can declare that the slope coefficient is not statistically significant. That is, the slope coefficient is not different to 0, and that there is no linear relationship between the independent and dependent variables. Okay? That is, the mean model is appropriate. You also consider this result as meaning that you cannot predict the dependent variable. Okay. Tandaan ha? Remember this? If the value of the p-value or the sig is greater than 0.05, then you cannot use that variable to predict the dependent variable. But since the value of the sig or p value is less of time in minutes spent watching TV is less than 0.05, then you can use this time in minutes spent watching TV to predict cholesterol. Tandaan, kung less than 0.05, magamit mo siya to predict. Pero kung greater than 0.05, then you cannot use this to predict. Substituting these values of the coefficients into the regression equation, you have cholesterol concentration equals negative 0.9. This is 0.027 times time watching TV plus or minus, 0.944. So in this case, gin-include niya pa gyapon, no? Even though hindi significant. Depends, no? So, but since in this reference, gin-include nila, so we will still include even though hindi siya significant. So therefore, kung gusto mo gamit sa X and Y, X is time watching TV, cholesterol concentration is the Y. So you could say Y is equal to 0.037X minus 0.944. So kung gusto mong, for example, since this is, you have now your prediction equation, no? If you wish to predict the cholesterol level of a person who watches TV for 180 minutes, so just change the time or substitute it rather with 180, and by substitution, you get negative 0.944 plus 0.7 times 180, or that's 5.72, this one, with this unit. Okay? And you could also have your write-up in this manner, integrating all the concepts we have discussed now. So feel free to read this on your own. And that's the end of the discussion. Thank you.